Hello, dear students. We now have solving wave equations using method of separation of variables. Here, we solve the wave equations by using the method of separation of variables. This is the general form of wave equation. It is partial square root of u by partial t squared equals to c squared partial square root of u by partial x squared. And here, x is from 0 to L and t is greater than 0. That means it's greater than 0. It's all the positive numbers. It could be all the positive numbers. And also, x tends to infinity because it's greater than 0. Here, the boundary conditions are u of x, u of 0t equals 0. Here, x is 0. That means we have x of, u of 0t equals 0. And also u of lt, u of L and t equals 0. And also we have the initial conditions, which are u of x0 equals f of x. And also u sub t of x and 0 is g of x. Here, u of x and 0 is f of x, but u sub t of x0 is g of x. Okay, here we have an example. It says use method of separation of variables to find the solution of the wave equation. Here we have given the wave equation, which is partial square root of u by partial t squared equals 4 partial square root of u by partial x squared. X is from 0 to 2 and t is greater than 0. And also you have given the boundary conditions, which are u of 0t is 0 and u of 2 and t is 0. And the initial conditions are u of x0 equals 2 minus x. This is f of x. If you compare to the above, to the general forms in the above, and this is f of x. And u sub t of x and 0 is 1. 1 is g of x. These two are f of x and g of x. Okay. Here, the partial differential equation is this one. We need to reduce the partial differential equation to ordinary differential equations. We let u of, this is the partial differential equation. First, let's write down it. U sub tt equals 4 u sub xx. Okay, this is the partial differential equation, and we let u of xt to be u as the same we did before in reducing a partial differential equation to ordinary differential equations. Here we let u to be x of x and t of t. This is x of x and t of t. Okay, x of x times t of t. Now we should find these partial derivatives of u of xt. We have u sub tt. We take the partial derivative for this function twice with respect to t. Here, x of x is a constant, so we just take two derivatives for t, which is u sub tt equals x of x times t double prime of t. Here we say it's prime because in function of t we have only t, we have no x in it. That's why we take its derivative. And u sub xx equals, in this case, when we take the partial derivative for the function with respect to x, t is a constant. T is a constant. G of t is a constant. So here we just take two derivatives for x. We get x double prime of x times t of t. And from now, I'm just going to write down x, capital X and capital T. I'm not going to write down x of x and t of t. Okay. When I'm writing down capital X, it means x of x. And when I'm writing down t of t means, when I'm writing down capital T means it's capital T of t. Okay. Now we'll turn these two to the partial differential equation. Our partial differential equation is u sub tt equals 4 times u sub xx. So that means it equals to x times t double prime equals 4 times x double prime t. Now we divide both sides by this number as we did before in all the other cases. This and x. We separate the variables. We put t with t prime and x with x prime. And also we divide by this number. Okay, we divide both sides by 4x capital T. And we get t double prime dividing by 4t equals x double prime dividing by x. And we say these two functions are equal in the only case, in the case if both are constants. So we say both to be lambda. Lambda is a constant. Okay. Now we equal each of the functions to the constant lambda. That means x double prime over x equals lambda, and t double prime over 4t equals lambda. And from these two equations, we can get that x double prime minus lambda x equals 0. This is a second order ordinary differential equation. And from the second equation, we get that t double prime minus 4 lambda t equals 0. We get these two ordinary differential equations. So in this step, we just reduce the partial differential equation to two ordinary differential equations. And both ordinary differential equations are second order homogeneous. Okay, it's linear second order homogeneous ordinary differential equations. Now, what we do here, we just try to find the boundary conditions for the ordinary differential equations from the given boundary conditions. We have given two boundary conditions, which are u of 0t equals 0 and u of 2t equals 0. We have these two boundary conditions, u of 0t equals 0 and also u of 2t is still 0. That means here, this is the x coordinate. Okay, this is the x coordinate. That means x of 0 is 0, and also x of 2 is equal to 0. As you see, this is 0 and this is 0. And these two values that we write down instead of x small are these two values which you have in the boundary condition. Okay. These are the boundary conditions. In our ordinary differential equations are x double prime minus lambda x double prime minus lambda x equals 0. And also t double prime minus 4 lambda t equals 0. We have these two second order linear homogeneous ordinary differential equations. We now work on the solution to find the solution for these two ordinary differential equations. Okay, we now have some cases. We say if lambda to be 0, here we said lambda is a constant. It's possible to be 0, to be positive, and to be negative. Okay, it could be positive, it could be negative, and it could be 0. So we take all cases and we choose the suitable case. We choose the case that we get a non-trivial solution. Here, for lambda to be 0, we say we have the ordinary differential equations. One of them is t double prime minus 4 lambda t equals 0. So if lambda to be 0, we get t double prime equals 0. And now what we do, we are going to find t by taking the integration for both sides. We get t prime equals, let's say, a. Let's use capital letters. Let's say a. And again, if we take another integration for both sides, we get t equals a times t plus b. We get a times t plus b. Here we take two integrations for t double prime equals 0. After taking two integrations, we get a times t. This is dt. This is dt. Okay, we get that capital T equals a times little t plus b. So here, as I said before, t is greater than 0, so it could goes to infinity. That means here, if t approaches infinity, in this case, sorry, so if t tends to infinity, what we get? We get that capital T equals infinity also. Here we get a times infinity plus b. Let me write down it. We get a times infinity plus b. So we get that capital T equals a times infinity is still infinity, plus infinity is still infinity. So you get capital T equals infinity. Or we can say, we can do it in another way. You see, from this, you say the limit of little t approach to infinity for capital T equals to the limit of little t approach to infinity for a times t plus b, and this equals to infinity. So it's not interested because t must not go to infinity. Yeah, we say it's not interested. Okay, that's it. This is for the case if lambda to be 0. We have two more cases. We say if lambda to be positive, we let lambda to be p squared. We let lambda to be p squared. If lambda to be p squared, here we have t double prime minus 4 lambda t equals 0. If lambda to be p squared, we replace lambda by p squared, and we get t double prime minus 4p squared lambda. Okay, this equals 0. And now this is a second order homogeneous ordinary differential equation. For solving this, we must find the characteristic equation. For the characteristic equation, we replace, so this is lambda, this is t naught lambda. Okay, here we replace t double prime by m squared. Okay, and t by 1. We get m squared minus 4p squared equals 0. And then we get that m squared equals 4p squared. And then we get that m equals plus minus 2p. We get these two distinct real values for m. That means m1 is 2p and m2 is negative 2p. Okay, so the solution is, say, t equals, let's say, a e to the power m1x m1 t, since we have a function of t, plus b times e to the power m2 t. These are m1 and m2. Okay, these are m1 and m2, and we get that t equals, I mean capital T equals a e to the power 2p t plus b e to the power negative 2p t. And also in this case, if a t approaches infinity, that means if t tends to infinity, let's see how about capital T. If little t tends to infinity, what we get? We get that the limit of t approaches infinity for capital T equals the limit of little t approaches infinity for a e to the power 2p times infinity times t plus b over, this is negative 2pt. So we return it to the denominator to become positive exponent here, b over e to the power 2pt. Now, if we put infinity for t, what we get? We get a e to the power infinity, because 2 times b times infinity is still infinity, plus b over e to the power infinity. E to the power infinity is still infinity. So b over infinity is 0. And this equals to infinity. That means t equals infinity. So it's not interested. It's not interested. It must not be infinity. Okay, here we say it's not interested. This is this case. We have only one more case. So in this case, we must have a suitable solution for the ordinary differential equations. Here we say if lambda to be a negative value, if it's negative, we let lambda to be minus p squared. Here p squared is always positive, and if we give a negative sign to it, it's always negative. Okay, it's always negative. Here we see limit of t equals infinity. Limit t approaches to infinity for capital T is infinity. That's why you say it's not interesting. We don't say t equals infinity. So if we approach to infinity for little t, capital T is infinity. Here we say for lambda to be negative p squared, it means lambda to be a negative value, t double prime minus 4 lambda t equals 0. It becomes, if you replace lambda by negative p squared, negative times negative becomes positive. We get t double prime plus 4p squared capital T equals 0. And now we find the characteristic equation. So the characteristic equation is, we replace t double prime by m squared plus 4p squared, and we replace t by 1. It equals 0. Now we find m. We say m equals minus 4p squared. So this m squared equals to that. And m equals 0 plus minus 2pi. It's complex because it's negative. When we put it into square root, we get a complex value. That means here alpha, this is the real part. I've written down this 0 for the real part. We just get this one. We just get plus minus 2pi. But we must have real and imaginary parts in a complex number. This is a complex number. Alpha is 0, and beta, which is the imaginary part, is 2p. Okay. Now we write down the solution, the general solution for this ordinary differential equation. Here, t of t equals e to the power alpha t times, let's say c1 cosine beta t, this is beta t, plus C2 sine beta t. Now we replace alpha and beta by the values here. Alpha is 0, so we get e to the power 0. E to the power 0 is 1. So this is gone. Okay? And here we replace beta by 2p here. And we get capital T of t equals C1 cosine 2p. And here when we take alpha and beta, we just take beta as a positive value. Here we say alpha plus minus I beta. We just take as the positive value, but if we have a negative sign for alpha, we take it. Okay, it's 2p C1 cosine 2p plus C2 sine 2p. This is, we have t also, 2p t. This is the general solution for t of t. Now we have another second order ordinary differential equation, which is x double prime minus lambda x equals 0. As we did before in the first step, we got two ordinary differential equations. So we must solve them both because u of t is the multiplication of these two. Here, x double prime minus lambda x equals 0. This is the second equation. This is the second ordinary differential equation. Now we replace lambda by negative p squared. Yeah, lambda is minus p squared. We have this case. If we replace lambda by negative p squared, we get x double prime plus, it becomes positive because here we have negative times negative is positive. P squared x equals 0. And then we solve this also. We solve this, we find the characteristic equation, and the characteristic equation is m squared, let me write down, is m squared plus p squared equals 0. And here m equals 0 plus minus p times I. Here alpha is 0 and beta is p. For solving for the general solution of differential equation, if it has two complex roots, we say x of x equals e to the power alpha x times, let's say C3 and C4. We use different constants for this one. In the previous differential equation, we used C1 and C2, and here we use C3 and C4. C3 cosine beta t, beta x, so not t, because here we have function of x, not for t, plus C4 sine beta x. This is beta x. Now you replace alpha and beta by their values. Alpha here is 0. Alpha is 0. If you replace alpha by 0, here we get e to the power 0, and e to the power 0 is 1. So this is gone. So x of x equals C3 cosine beta here is only p. Beta here is only p. It's px plus C4 sine px. This is the solution for this ordinary differential equation. Now we have two boundary conditions for this differential equation. The boundary conditions that we found in step 2, let's return to step 2. These are the boundary conditions. We apply these two boundary conditions to find the value of constants. To find the value of constants, which are C3 and C4. The boundary conditions are x of 0 is 0, and also x of 2 is 0. We have these two boundary conditions. For the first one, we say x of 0 equals 0. That means if you replace here x by 0, let's see what you get. If you replace x by 0, we get x of 0 equals C3 cosine p times 0, which is 0, because we replace x by 0, plus C4 sine p times 0 is still 0. Here, sine 0 is 0. So this term all becomes 0. And here, and this also equals 0, because here we say x of 0 equals 0. We replace x by 0, then we equal to 0. And cosine 0 is 1. And in this case, we get that C3 equals 0. This is for C3. That means C3 is 0. So now our ordinary differential, our solution becomes, this is the solution. Okay? If C3 is 0, we get that x of x equals, if C3 is 0, so this term becomes 0. You just have C4 sine px. Now we apply the second boundary condition. And here we get that x of 2, the boundary condition is x of 2 equals 0. Here, in this solution, we replace x by 2 and it equal to 0. We get x of 2 equals C4 sine 2p. C4 sine 2p. And now, we say this equals 0. C4 must not be 0, because if it's 0, so x is 0. The solution for x is only 0, which is the trivial solution. We don't have to get a trivial solution. We must look for a non-trivial solution. Okay? C4 must not be 0, so this term must be 0. In which of the angles sine is 0? If this n pi, it's 0. Sine of n pi is 0. That means we equal the angle to n pi. Okay? We say 2p from this, we say C4 must not be 0. It means 2p equals n pi. It must be n pi, because sine of n pi is 0. You see, the sine function must be 0. That means here the angle must be n pi. So 2p equals n pi. That means p equals n pi over 2. This is the value of p. Now we return it to this one. So this becomes x of x equals C4 sine, we replace p by n pi over 2. Get n pi over 2x. This is the solution for x of x. Okay? This is the solution of x of x. Now, we replace p by n pi in the solution of t. This is the solution of t. Here we found here. We replace p by n pi over 2. We replace by n pi over 2. The solution is t of t equals c1 cosine 2pt plus c2 sine 2pt. So t of t equals c1 cosine 2pt plus c2 sine 2pt. Here, we replace p by n pi over 2. If we replace by n pi over 2, what you get? We say t. We say if p to be n pi over 2, what we get? We get that t of t equals c1 cosine. If we replace p by n pi over 2, we get 2 times n pi over 2. These are cancelled out, so you get only n pi t. Okay, I'm just going to cancel out here in this step. Cosine n pi t. plus C2 sine 2 times P is n pi over 2 T. These two are cancelled out. We get only n pi T. This is T of T. Okay, this is T of T. So we have these two solutions now. But here we still have the initial conditions. We must apply the initial conditions also. So the sum of all cases, we say lambda to be 0 and lambda to be greater than 0 are not interested. These are not interested. But if lambda to be less than 0, we get these two solutions. X of x equals, we write down it. This is x of x. C4 sine n pi over 2x. The C4 sine n pi over 2x. And T of T equals C1 cosine n pi T plus C2 sine n pi T. We have these two solutions in the case of lambda to be less than 0 or lambda to be a negative value. We now apply the initial conditions. Here we have the equations are here. Okay, we have these two equations. We say, let's return to above with the given example here. It says u of x and 0 is 2 minus x. This is f of x. But here we have that u sub t of x and 0. That means if we take the derivative for t with respect to t and then replace x by t by 0, we equal it to 1. Let's write down first the initial conditions. Let me see. U of x0 is 2 minus x. And u sub t of x0 is 1. We have it's too long. U sub t of x and 0 is 1. That means here, this is t. We take, this is little t. Little t is 0. And we take the derivative of u, which is x times capital T, capital X times capital T. We take the derivative for u with respect to t. That means we get t prime. Here we say t prime of, here t is 0, equals 1. This is the initial condition. This is the initial condition. We now find t prime. We now find t prime. Here, let's come to here. Make a little bit smaller to see the other one. T of t, let's write down t of t. T of t equals C1 cosine n pi t plus C2 sine n pi t. We have this solution for t. Now we must find t prime of t. Then we apply the initial condition. T prime of t equals, we take the derivative for cosine, it becomes negative sine, negative C1 times n pi sine n pi t, and derivative of sine is cosine, plus C2 times n pi times cosine n pi t. Now we apply the initial condition. We apply here, let's see in the above. This is the initial condition. It's the initial condition, which is t prime of 0 is 1. Here we took the derivative for t with respect to t. Then we replace t by 0 equal to 0. Apply the initial condition, which is t prime of 0 equals 1. Here we replace t by 0 and we equal it to 1. We equal it to 1. Here, let's see what we get. We get that t prime of 0 equals c1 times n pi times sine 0. Here, if we replace t by 0, we get 0 plus c2 times n pi times cosine 0. Sine 0 is 0, so this term all becomes 0. Okay, all this term becomes 0. That means here we put this to 0. This is c2 times n pi cosine 0 is 1 times 1 equals 0. Here n pi is not 0, it's constant. It's a constant. That means c2 must be 0. c2 equals 0. So if c2 equals 0, so c1 must not be 0. That means t prime of 0 equals, let's write down t of t here. In t of t, in this one, we replace c2 by 0. If we replace c2 by 0, what we get? We get c1 cosine n pi t. This is t of t. And previously we found x of x, which is c4 sine n pi over 2x. We say u of xt equals x of x times t of t. We let this be at the beginning. Now we replace x and t by their functions. X of x is c4 sine n pi over 2. It's c4 sine n pi over 2x times c1, this is t of t, times c1 cosine n pi t. This is u of x and t. So here we say un of xt equals, we multiply these two, which is c1 and c4. We let c1 times c4 to be bn. Okay, we let c1 times c4, let c1 times c4 to be bn. In wave equation, we always need to find bn. Okay, and here we get bn sine n pi x over 2 plus, so times cosine n pi t. Here we work on f of x. We have given f of x in the example. We have given that u of x and 0 is 2 minus x. This is f of x. This is f of x, which is 2 minus x. Let's write down f of x here. And u of xt, we can write down this as a sum. And from 1 to infinity, because here we have b and we have not a. Okay, in wave equation, we always must find bn. So the series is starting from 1 to infinity. It's not starting from 0 to infinity because it's Bn. If it is An, we must start from 0. So we have A naught and An. Okay, but here we must only find Bn. It's Bn sine n pi x over 2 times cosine n pi t. And so, yeah, we should find Bn. It's a Fourier series. In Fourier series, but let's see about the values of L. As it is given, this is x from 0 to L. X is from 0 to 2 as half range Fourier series. As a half range Fourier series. So L here is to, if we compare to the above one, L, if you compare to this one, L is 2. It's from 0 to 2. Let's written down. Yeah, we find Bn. We see Bn is 2 over L. Let's write down f of x is 2 minus x, and L is 2. These are given in the exam. 2 over L times the integration from 0 to L. For f of x times, to find Bn, we multiply f of x by sine n pi x over L. Sine n pi x over L. We replace L and f of x by their values. And we get that Bn equals 2 over 2. L is 2. L is 2. This is minus x. It's 2 over 2, since L is 2. Integration from 0 to 2. For f of x is 2 minus x times sine n pi x over 2. We have this. Now we find this integration. These two are cancelled out. So Bn is the integration from 0 to 2 for 2 minus x for sine n pi x over 2. This is dx. I forgot to write down dx here and dx here. We find this integration. We can use integration by parts, or we can use the short method. We let d to be 2 minus x, and we let the integration to be sine n pi x over 2. Okay, and we find the derivative for 2 minus x. The first derivative is -1, and the second derivative is 0. So you must take two integrations for for sine n pi x over 2. The first integration is -2 over n pi minus 2 over n pi cosine n pi x over 2. And the second integration is -4 over n squared pi squared times sine n pi x over 2. We multiply these two, then minus, we multiply these two. And we get, I'm just going to write down the result of the integration, the final result for the integration, which is 4 over n pi. We get 4 over n pi. Now we return Bn to the series. We get u of xt equals the sum from 1 to infinity n equals 1 to infinity. For Bn is 4 over n pi. It's 4 over n pi times sine n pi x over 2 sine n pi x over 2 times cosine n pi t. This is the solution. This is the solution for the given wave equation. It's actually too long, but it's not difficult. It's not difficult. There are a lot of steps here, but it's not difficult. And all the wave equations are going to be solved in this way. All the wave equations are going to be solved in this way by using the separation of variables. And we now have solving Laplace equation by using method of separation of variables. Yeah, we can solve Laplace equations by using method of separation of variables. It's similar to the above one. Here, only the equations are changed. We have partial square root of u by partial x squared plus partial square root of u by partial y squared equals 0. This is the Laplace equation. This is the Laplace equation. X here is from 0 to a, and y is from 0 to b. Yeah, we have given these two intervals for a and b. With the subject to the certain boundary conditions, we must have given the boundary conditions. We can see the equation has no dependence on time. Here, it's not dependent on time. It only depends on x and y. X and y are none of them are time. So here, it's not dependent on time. But the previous one, for the wave equation, it depends on time. It depends on time, as we did in the case of lambda to be 0 or lambda to be positive. We got that if t tends to infinity, we get capital T also tends to infinity. It depends on time. But here, Laplace equation is not dependent on time. It's no dependence on time. So just on the special variables x and y. We have only variables x and y in it. This means that the Laplace equation describes steady state situations, such as we say steady state temperature distributions, steady state stress distributions, and steady state potential distributions, and so on and so on. Here we have given an example. In this example, we have given a square plate is bounded by x to be 0 and x to be a, and y to be 0, y to be a. We have this plate. Let's draw it. X from 0, let's say it's a, and y from 0 to a. This is the plate. You see, a plate is bounded by x to be 0 and x to be a. This x and this y. Okay, y from 0 to a. This is the plate. This one is the plate. It says apply the Laplace equation. This is the Laplace equation to determine the potential distribution u of xy over the plate subject to the following boundary conditions. Here we are asked to find u of xy. So you must find u of xy. And we also have given these boundary conditions. Okay? And these also. We have given these conditions to the Laplace equation. Here, where u naught is a constant. U naught here is a constant. Let's say it's a, b, c, and any constants. Okay? But we write down it as u naught. Also, show that the temperature at the center of the plate is given by this. So the center of the plate is this one. And this point is a over 2 and a over 2. Here, after finding the solution for the Laplace equation, we replace x by a over 2 and y by a over 2, and we get this result. We just get this result directly after finding u of x. Here we get u of xt, u of xy, sorry. After finding u of xy, we find u of the center of the plate. This is the center of the plate. It's a over 2 and this is a over 2. So this point is a over 2 and a over 2. X is a over 2 and y is a over 2. We replace each x and y by a over 2 and get that u of a over 2 and a over 2, which is the center of the plate, is u naught sine hyperbolic of pi over 2 dividing by sine hyperbolic of pi. Okay. Here for the solution, we do the same as we did before for wave equation. So here we're going to find the, or we'll reduce the partial differential equation to two ordinary differential equations. We say u sub tt, this, sorry, the u sub xx, not tt. U sub xx plus u sub yy equals 0. This is our partial differential equation, which is the Laplace equation. We let u of xy to be x of x and y of y. We should find u sub xx and u sub yy. We say u sub xx as x double prime y, and u sub yy equals x y double prime, capital Y double prime. We now return to the partial differential equation. We get x double prime y plus x y double prime equals 0. And we move, we divide both sides by xy first. Let's divide both sides by xy to write down x with x and x with x prime and y with y prime. If we divide both sides by xy, we get x double prime of x equals y, sorry, minus, plus, not equals. Plus y double prime of y equals 0. Now we move this to the right hand side. You get that x double prime of x equals y minus y double prime of y. And you say these two equations are equal in the only case A, both are constant. We let them to be lambda. Okay. Now, here we find the boundary conditions as we did before. We find the boundary conditions. Then boundary conditions as we find or found in the previous example. Okay, that's it. Now we have three cases for lambda. After equaling this to that, here we get x double prime minus lambda x equals 0. And also y double prime plus lambda y equals 0. We have these two differential equations, second order ordinary differential equations. We solve those two second order ordinary differential equations. In the case if lambda to be 0, it's not interesting, and we don't get a non-trivial solution. Okay, or it's not interested. In this case, it's not interested. It's the same as before. Okay, and here it's not also not interested. In the last case, which is if this minus b squared, we don't say it's minus b squared. We can say it's n squared pi squared, and n squared pi squared is also a constant. Also, we can say it's b squared. We let lambda to be minus b squared. In this case, we get a solution. we put negative p squared for lambda in both ordinary differential equations and solve both differential equations. Then we get the results. Okay, it's homework for yourselves. Do it by yourselves, and it's easy and similar to the previous example. We solved some examples in like this. It's for yourselves.